Dear students, in the last class we studied about the resonance and when the resonance will happen, how it look like, okay, what will happen in the resonance, what are the tuning circuits we have studied. So today we are going to study the quality factor. What will be the quality of that resonance? Okay, so we'll start it with an example also, and this quality factor is also called as sharpness, right? So okay, and today we will be hearing some music in the background because some students are playing music in another room, so don't concentrate on the music. Okay, so this is the curve. This curve is called frequency response curve. Frequency response curve. In one axis there is omega, that is angular frequency, and another one axis there is the current I. Okay, so and this black dotted line is the oscillation of the current when there is no resonance, right? So we know that the current AC current will oscillate like this. So this is the part that I am showing over here. I am not showing this one. Okay, so this will be enough to explain what is sharpness and what are the quality factors. Okay, so understand this quality factor and sharpness. Let us go to again the same example of radio. Okay, so we have got the radio here. What is this? This is a radio, which is a tuning circuit in which there are LCR circuit, LCR series. Okay, I will write series LCR circuit is there, and there is some antenna, and this antenna there are so many frequencies which are coming. For an example, this is say 90 megahertz frequency, okay, and this is say 95 megahertz frequency, and say this is say 101 megahertz frequency, which is coming towards this tuning circuit or the radio from the different stations, from different radio stations. Now what we do is that I will tune this. Whenever I tune it, it will have a natural frequency. Say it has got the natural frequency, say it has natural frequency of 95 megahertz. Okay, and there are three different signals from the three different radio stations, right? Now whenever I tune it, that is, I am changing the frequency, and whenever this frequency matches with this external radio frequency which is coming towards this radio, which is capturing by this radio, that time we say that this circuit is in the resonance, and that time the resonance frequency would be omega naught equal to 95 megahertz. This is an example. You can write it somewhere in your copy. It will be very helpful. That time what we say is the current in that circuit will be very large. The amplitude of the circuit will be very large, as given is in this frequency response curve. The red line is this one. Okay, so this is the I0, that is the maximum current, and I will write this as resonance. Why I am writing this as resonance? Because this I0 is the maximum current in the resonance. It is just like this. Okay, I0 resonance against it. So this will be P of 0, maximum power. Okay, because if the current is maximum, the power will be maximum, very sure, right? So but whenever we tune any radio, what we know is that before listening to the very clear sound, we hear some other sound also. We hear that sound as well as some noise, right? Whoosh, 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 and that sound, and that sound. These are the noises. Okay, and say from which point we will get that noise. Let us see in the graph. So I increase this omega in the radio. For an example, 95. This is 95 here for an example only. But before 95, what are the values? There are 94. Okay. There are 92. Okay. There are 91. There are 88, and so many frequencies are there. Okay. And at 95, I will hear the clear sound. But what about 94? What about 94.6? What about 94.9? It is almost about 95. Okay, in very close range of this resonance frequency, I will also hear some sound but with the noise. Example, let this be the point, okay, let this be the point after which I will hear the sound but with the noise. I will draw here also, upper part also, here. What is this? This is omega 2. Now in between omega 1 and omega 2, what I hear is, I will hear the sound of the radio, in the radio, but that sound could be very noisy and it could be very clear. When it will be very clear? When this will reach omega naught, there will be resonance and will get very clear sound. But what about this and these values? In these values from omega 1 to omega 2, this is a certain region in this omega in which we hear the sound, but that sound could be noisy as well as clear in between them. Okay, here no sound, okay, here no sound, here no sound, but here is sound, and here is noisy, less noise, very clear. At this omega naught, very clear, noisy, very noisy, and no sound of that channel. Okay, so this is how it look like. Now these points of the frequency will be called as bandwidth, BAND, bandwidth, WIDTH. So what do you mean by bandwidth? Bandwidth is that length of the frequency. Bandwidth is that length of the frequency within which we hear the sound, but that sound could be clear or with the noise. And that sound could be very clear when the frequency is omega naught. Apart from the omega naught, in between omega 1 to omega naught and omega naught to omega 2, we will hear the sound but with the noise, and that region of that length of frequency is called bandwidth, right? Okay, so this is all about the bandwidth and the frequency. So let me go to here. If I draw it, this line, what do I get? This is some value of current. Okay, below here, this point, if this is the current, if I say this is the current which is less than omega naught, will there be any sound? No sound. But whenever I reach this omega 1, I will get a particular value of current. From this current onwards, I will be able to listen the sound. Okay, this was in terms of frequency. Now this will be in the terms of current. Now this current is exactly I naught by root 2. Okay, so what is I naught by root 2? This is IRMS. We have studied. Okay, IRMS is equal to, this is equal to I naught by root 2. Okay, when the current is I naught by root 2, after that we will hear the sound, that is in terms of current. Here, if current is less than I naught by root 2, I will reach here and I will come here, which is less than omega 1. Okay, we will not hear any sound, but we will hear only the noise. What I mean is, only the noise will be there below this omega, but we don't hear the sound. But after this omega, there will be sound as well as the noise. But at omega naught, there will be only sound, no noise. And after this omega 2, there will be only the noise, no sound. Okay, so this is the region. Alright, now whenever I go above, if the current is larger than I0 by root 2, then I will hear the sound but with noise. If the current is here, then there will be current and there will be omega. This omega is greater than omega 1, so I will hear the sound, but that sound will be noisy. And whenever I reach here, this is the maximum current. If there is maximum current, then there is maximum power. Then if I reach the maximum current, the corresponding omega is omega naught. That is, I will hear the clear sound. Now, there is some problem with this. What is that problem? That whenever we tune the radio, there is always some noise, and we don't want to listen the noise. Now, how do we reduce that noise? So where are the noise? Noise is in this region. Omega 1 to omega naught is region, and omega naught to omega t is the region where we have got the so many noises. And whenever we want to reduce the noise, what we need to do? We have to excuse this. Please write. We have to excuse this. It means that to reduce the noise, we have to decrease the bandwidth. This is very long bandwidth. Now, if I come very close, the bandwidth will be decreased. Now, whenever we decrease the bandwidth, we get the good quality of sound. Okay, so we are going to study sharpness and quality factor now. Okay, so to get the good quality of sound, to get less noise, what we need to do? We need to we need to shorter the bandwidth. Now, what will happen if I shorter the bandwidth? Let us see in this graph. Okay, so this is the graph where I will shorter the bandwidth. I will make the bandwidth very, very short. This is I only, and this is case 2 at resonance. Okay, this is also the for the resonance, at resonance with flat curve. The curve is very flat, not the very sharp. Here with sharp curve. Now you will be understand this. It will be looking like this. This is something like this. Now, whenever I decrease the bandwidth, I will hear no noise. Okay. Now whenever I decrease the bandwidth, the curve will become very, very sharp, isn't it? This curve has become very, very sharp. So this is the sharpness. Whenever the curve is very sharp, what will be the quality of sound? Very, very good, because there will be no noise. Here is noise. All this is noise. Okay, this is noise. There is noise. This is noise. This is also noise. Okay, noise plus sound. Okay, noise plus sound. Here only noise. Only noise. Here only noise. This region, noise and sound, there is some region, so we hear some noise. But here what I do is, now I will take the peak value. This is I0. Okay, and this will be, let us consider as this as my I0 by root 2. For this, what I do is, I will take this graph down here. This is omega 1, and I will take from here down. This is omega 2, and from here I will take the peak value exactly at the resonance, and this will be giving me, this is my omega naught. This bandwidth here, bandwidth is very small. Okay, whenever the bandwidth is very, very small, then we get very clear sound. So if you see which will give the good quality of sound, this graph or this graph will give the good quality of sound, because it has very less bandwidth. Okay, these are all about this. So this is case 2 for the same circuit. This is for, if this is for the radio 1, and this is also for the same radio. Okay, but here I have changed the bandwidth. So here we get good quality, here we get bad quality. Why? Because the region of the noise plus sound here is this much, but here region of the noise plus sound is very, very less. Okay, if the curve is very sharp, we get good quality of sound, but if the curve is very flat, we don't get the good quality of sound. So Q factor, let us go. What are the factors on which the quality depends? Please write, what are the factors on which the quality of sound depends? That is, if the bandwidth is very, very small, we get good quality of sound, no noise. If the bandwidth is very large, we get bad quality of sound with lot of noise. Okay, so let us find some mathematical formula to see when this curve will become very small and when this curve will become very large. Okay, so the topic is quality factor or sharpness. So this is omega. So the topic is quality factor. Q factor भी कहते हैं इसको, ठीक है? The quality factor is defined by Q is equal to voltage across inductor divided by voltage across resistance, or Q factor is defined as voltage across capacitor or voltage across resistance. Okay. So in this graph I will explain one more thing also in the later part. So this is going to be my quality factor. So there are two definitions. VC by VR is also quality factor. VL by VR is also quality factor. What is VL? It is potential drop across the inductor. What is VR? Potential drop across the resistor. What is VC? Potential drop across the capacitor. Because in series LCR, what happens is we have this, isn't it? So here is VR, here is VL, here is VC. Okay. So then this will be become how much? This will become I into R. This will be okay. What is VL? This is what is VR? This will become I into R. Okay, this will become I into resistance is my X of L. This will become I into X of C, isn't it? V is equal to I into R. So here the resistance offered by this inductor is XL, inductive reactance. So it will be my XL. This is I. This will be I and R. Isn't it? Now it is done. But we are doing here for the resonance. In the resonance, there the current will be maximum. So I will write I0 here. This will be I0, and this I and this I will cancel, and I will get XL by R. So Q is equal to XL by R. So the formula of XL is, we know XL is equal to omega L. So I will write this Q is equal to omega L divided by R. Again we are doing it for the resonance. At the resonance the omega is omega naught. So this will be omega naught L by R. So this is the Q factor. Now tell me when the Q factor is large. Q factor large. What do you mean by if the Q factor is large? If the quality is large, then sound is very good. Okay, if the sound, when the sound will become very good, if this curve is very, very sharp. Okay. So to have very high quality, what should be the resistance? Resistance and quality is inversely proportional. If the resistance is very, very small, then quality will be large. Quality large means sound will be clear. Sound will be clear means there will be very sharp. Okay. Now to have very sharp curve or have to good quality of sound, the resistance on series LCR, this should be very, very small. What should be the L? L and Q is directly proportional. So the inductance of the inductor has to be very large. If this L is large, Q is also large. If the Q is large, quality is good. Quality good means sound is very clear. Sound very clear means this is very sharp. Curve is very sharp. The curve sharp means bandwidth is very less. So please write each and everything. Okay, it will be very, very useful. Okay, so I will also go to the one more equation over here. Okay, because the omega naught is equal to 1 by under root L and C. Okay, let me put this here in quality, or Q is equal to how much? There is omega naught, there is L by R. I will write L divided by R is there, into then omega. Omega is 1 by root of L into C under root. So this L under root L will cancel this root times, and this will be giving me how much? This will be implies this Q is equal to, this is 1 by R is there. Okay, and this is L by C. This is also under root. This is also under root. So this will be this one. Okay, so what do we got in the final? Q factor quality is equal to 1 by R root over L by C. Okay, so when the capacitor is very small, the quality is very less. Another thing is that this capacitance of the capacitor in series LCR should be very small. If this is small, Q will be large. If the Q is large, quality is good. If the quality is good, sound is good. If the sound is good, curve is sharp. If curve is sharp, the bandwidth is very small. So this is all about the sharpness and the quality factor, and it is very easy. So let me add some more point here. Okay, When the I0 by 2, when I0 by root 2 is there, after that we will hear the sound with noise. Okay. Now this can be also said as when the power is maximum by 2, after that, this is also here I will also write power maximum by 2. Okay, this is maximum power P0, P0 is maximum power, very clear sound. When the power is half of the maximum, P0 by 2 is half of the maximum. When the power is half of the maximum, when the power reaches half of the maximum, after that, from this above, we will hear the sound with noise. Okay. So this is also we can also derive P0 by 2. When the value of current is I0 by root 2, the power will be exactly half of the maximum. So let me derive it. Okay, you can write this note in the side of your copy. So let us see, the power is equal to IR. We know power is IR. So let me write P is equal to, whenever we calculate anything, whenever we calculate power, we only take what? We take the RMS value. Okay, whenever we measure current, we take RMS value. Whenever we measure voltage, we take RMS value. So this I will be my IRMS. So IRMS is equal to how much? It will be, okay, this is I square R. Okay, power is I square R, and this will be RMS will be I0 by root 2 whole square is there, because of this I square, and there is R. So this is IRMS will be equal to I0 square into R divided by 2. This is power, right? I0 square by root 2 को square क्या होगा? Root 2 का square होगा 2. Then what is this value? I0R is power. I square R is power. I0R will be what? This power will be P max by 2. Understood? When the power is P max by 2, P naught by 2, after that power we will be able to hear the sound. Okay, it may be very clear or it will be with the noise. Okay, so this is all about this. So we got P0 by 2. Why getting P0? Because I0 is there. If this is I0, then it has to be P0. So when the current is I0 by 2, the power is P0 by 2. So this is all about, we did so many things. We did for power also, we did in terms of I0 also, we did in terms of omega also, and sharpness and the quality factors. With this, we end this topic. Thank you.